Hello and welcome to lesson 21, where we are now looking at our third type of special function and its derivative. So our logarithmic function. And especially now that we've seen the exponential functions, we're going to be making a lot of connections to that function and its derivative. So before we jump in, we are reviewing some properties of logarithms because we are going to be using those. So please take a moment to review all of these. Specifically, you'll see me use product rule, quotient rule, power rule, and we are going to use the change of base rule as well to make conclusions about the derivatives of the logarithmic function. So let's start with the concept of inverse functions. And we already talked about this when talking about exponential functions because we analyzed the logarithmic function as an inverse of the exponential function. So what that means is when two functions are inverses of one another, then the one function is reversing the action of the other. So if we have the function f of x, which maps x to y, then the inverse function, which is denoted f to the power of negative 1y, and notice now here the input is y, because it maps y back to x. So it's doing the reverse action. And so the input and output values are now exchanged, and that's what we also saw last time, where the domain and range values were exchanged. And the original function f of x is reflected across the line y equals x to get to that inverse function. And again, we saw this with the exponential as well. So now if we have two functions, f of x and g of x, that are inverses of each other, then the derivative g prime of x is actually 1 over f prime of g of x. And again, this comes from this definition over here. And you don't actually need to analyze this or find the proof of it for the time being. We can just take it as is, and we're just going to use it and apply it to find the derivatives that we are looking for. So I want you to think, how would that definition up there, so inverse functions and their derivative, help us to determine the derivative of the logarithmic function? And specifically think about our previous lesson. So starting with our natural exponent function, so our exponential function for the Euler number, which is f of x equals to e to the power of x. And we know that this is the inverse of the natural logarithmic function, or the logarithm function is the inverse of the natural exponential function. And so g of x, which is the natural log of x, is the inverse to f of x here. And so g prime of x, based on that definition up there, is equal to 1 over f prime of g of x. But this would just be 1 over e to the power of g of x, because f of x is just e to the power of x, and the derivative of that is just itself. And g of x itself was the natural log of x, so we just substitute that back in. But this also is a special property, which we know is equal to x. So then the derivative is just 1 over x. And so generalizing that now as a definition, the derivative of the natural logarithmic function, f of x is equal to natural log of x, is given by f prime of x, or d of natural log of x by d of x, is equal to 1 over x. And we do have to have that x is greater than 0. And consider here why we already know x is not equal to 0, but thinking of the inverse, its inverse function, which is, f of x is equal to e of x, we do have to consider the domain there to consider the, the range here to consider the domain here. Now, we saw this for the natural logarithmic function, and I want you to think how we can extend this to any logarithmic function and what the derivative of that would be. And specifically, your hint here is to use the change of base formula. So using the change of base formula, we have that the logarithm of a with a base b can be written as log of a base c over log of b with base c. So we now introduce that new base, which is c, and then we have a in our numerator and b, which is our original base in the denominator. Now, rewriting this with Euler's number, and remember that log of e is actually just the natural logarithm, right? And so here, what I did was rewrite this as log of e x over log of b, or sorry, log of e, and then x, or b, b. Okay, there we go. And so these two parts are just the natural log. And so we have this definition here. Now taking the derivative of both sides, because this is the derivative we want to find, right? Now we have to find the derivative of the natural log of x over natural log of b, and we're finding the derivative of this with respect to x, so our variable x. But notice how natural log of b is not dependent on x, so it's a constant. So we can factor that out. That's our constant multiple rule. And now we're left with the derivative of the natural log of x. And based on our definition, we have that this is equal to 1 over x, and then we're just left with that natural log of b. And I hope you can see this is pretty much the same idea as the exponential function that we had, where we just multiplied by the natural log of b, and we are just keeping that derivative 1 over x. Now, let's generalize that as well to have our definition. So the derivative of the logarithm function, and this can be any base now. We're not defining our base as the Euler number. So if we have f of x is equal to log of base b of x, then the derivative of this, which is also in Leibniz notation here, is 1 over x times a natural log of b. And again, we do have x is greater than 0 here. So let's try now, because we defined this, but now you might be thinking, why is this useful? What am I going to do with this? But it actually does have a very it's going to be a very useful tool for us in differentiating specific functions. So let's start with our first example here, which is y equals x to the power of x. So here you do have a power, but we can't actually apply the derivative power rule because the power is a variable itself. It's x. So we can't just do x and then x times x minus 1. We can't do that. So we need to find another method. So what we're going to do is, and you have to trust the process here, but we're going to take the natural logarithm of both sides first. So we have y on the left side and x to the power of x on the right-hand side. So I take the derivative, or sorry, the natural log here. So natural log of y, and then the natural log of x to the power of x. But using logarithmic rules, I now can take that exponent x and make it a coefficient here. So now looking at, let me highlight it, maybe these two terms here as an equality, we're going to differentiate both sides. So on my left-hand side, I have d of a natural log of y by dx and this derivative on the right-hand side. And this is the one I'm going to start with. And we're going to find the derivative of the left-hand side and right-hand side separately and then combine them to find our original derivative. And remember, our original derivative that we were trying to find based on this function here is dy by dx. So now, looking at the left-hand side, we are applying the chain rule with our definition of the derivative of the natural logarithmic function, which is going to give us, for a natural log of y, 1 over y, and dy over d of x. So this is just that definition, and then we have to apply the chain rule here, which is dy over dx, and that's exactly the derivative we want. But we're not done yet because we still have unfinished work. And this is just y prime as well, just different notation. Now on the right-hand side, I have x times natural log of x. This is our product rule. So we have to find the derivative using product rule. So we have x times the derivative here, and then the derivative of x times natural log of x. And this here is 1 over x, So that's why here I have x over x. Because of this x and this x in our fraction, we have x over x, which is just going to be 1. And for this part, I have 1 here and just natural log of x. I can't do anything with that, so all I'm left with is 1 plus natural log of x. Now, putting the left-hand side and right-hand side together, this was my left-hand side, and then this is that right-hand side. And I actually just want this derivative here. So I'm going to multiply by y here and just keep my 1 plus natural log of x. Now, y was actually x to the power of x. So we're just substituting that, and now we are left with y prime is x to the power of x and times 1 plus natural log of x. And I'm sure looking at it now, you can see that you wouldn't have been able to find this using any of the methods we've been learning so far, just from up here. And so now you saw how this, the derivative of the logarithmic is able to help us find the derivative of specific functions that are maybe too complex. Let's look now at another example. Here we have y is equal to x to the power of 3 times natural log of x. This is a chain rule of our exponential function, but we just have a more complex exponent here. So I'm actually going to do a different method for this one, and it's our change of variable. So given this exponent, I'm going to do a change of variable and let u equal to that exponent. And so now, if I'm finding the derivative of y, using change of variable, this is dy by du and du by dx. And so y itself can be written as e to the power of u, given this definition of u. Now, taking the derivative, and all I'm doing now is just substituting that u here to find the derivative, the definition there, and then just finding the derivative with respect to u. So in the first part, this is my derivative with respect to u, so I'm not changing anything. That's my definition of the derivative of the exponential function. And then for this part, we actually have a product rule here because it's x cubed times natural log of x. So that's why I have that bracket there. So using the product rule, we have those two terms, and we're finding the derivative of the first term here and the derivative of the second term, and just multiplying it by the remaining term. And so here, this is just my power rule, so I get 3x squared. And over here, this is just 1 over x by our definition that we saw today. And so multiplying this by that x cubed, I am left with x squared here. And notice how I had x squared here as well. So when I'm rewriting it now, I can try to simplify my expression. So I factor out that x squared there, and I'm left with the same coefficient I had here, just x squared is added. And then inside my bracket, I have 3 times natural log of x plus 1, because this would have just been equal to x squared. And so here we aren't necessarily using the derivative of the natural log to make our lives easier or make our derivative differentiation easier, but it was used in our function itself. So we have to know what the derivative is in order to apply our product rule and chain rule and be able to find our final derivative. Now, same with this one. It's just we're not using the derivative to as a technique. We're just using it by its definition because we have the function itself. But here we have now a composite function of the natural log. So we do have our outer function as the natural log function, and then our inner function is a polynomial. And so using a change of variable here, I'm going to, and you don't necessarily have to if you are thinking of this as chain rule, you can just skip to this part right away, but just so you can see it visually a little better, I am showing you with a change of variable. So I'm going to define u to be my inner function, and that's the polynomial. And so f of x, which is just y, is now equal to natural log of u. And so with our chain rule and change of variable here, I have that the derivative of f of x, or this is just derivative of dy by dx, then this is just equal to d of natural log of u by du, and then d times du by dx. This part here is just 1 over u based on our definition, and then the derivative of the polynomial is just 10x minus 3, which you can see from here. And now I will have one last step, which is to substitute that value of u here. And so now I am left with a rational function here. And again, you can just leave this as is. We don't need to work on, we wouldn't be able to simplify this any further anyways, but just leaving it as is fine. So now I'm just giving you a key idea, and this is back to example 1 of when we did use the logarithmic differentiation to help us differentiate maybe more complex derivatives. And then we're going to do an example for this as well. So if you have a function y equals f of x, we can actually differentiate this by first taking the natural logarithm of both sides, and we would get natural log of y equals natural log of f of x. Then we can actually use logarithmic properties or logarithmic rules to simplify the expression. And then we have to differentiate with respect to x. And remember our original derivative is y prime of x, which is dy by dx. So you'll see that somewhere in this differentiation, but not explicitly. So then you have to do a little bit of simplification and solving and moving things around to be able to solve for y prime. And then sometimes in your final expression, you'll have that y still there. So you will have to substitute back the function itself so that you don't have y prime is equal to an expression with both x and y. We only want the variable x in our derivative function. So now let's see what that would look like. So we are given this following function, which is a big rational polynomial. And if you try quotient rule or product rule here, it'll take you a lot of steps because it's there's multiple functions here, and so you have to do multiple steps at a and it would just take a long time. So we're going to now use this process here to speed up our work. So first we're going to take the natural logarithm of both sides. So then here we have natural log of y, and then the natural log of this whole rational function here. Now, the logarithmic quotient rule tells us that when you have a fraction, so something divided by something else, then this is just a subtraction of the natural log. So that's what I've done here. We have our numerator and then our denominator, and they're being subtracted. And similarly, the product rule also tells us that if you have two terms that are being multiplied by each other, then you can just take the natural log of each and add them together. And that's exactly what we are doing here. And this I've done inside the bracket because I'm going to distribute this negative after. And finally, we have also the power rule, which tells us that if you have these exponents here, then they can just become your coefficients. So this 3 is my coefficient, the 9, the 8, and the 4. And here I've also distributed that subtraction there. So we have -8 and -4 here. Now I have 4 terms, and I can differentiate with respect to x. And on the left-hand side, I will have, and again, this comes from d of, which is going to give me 1 over y times dy dx. And this is just y prime. So that's why I have y prime over y. And now, in these terms here, first thing I want you to notice is how we have x plus 3 in the denominator, 2x plus 7 here, x here, and 4x minus 3 here. And that's just your derivative of the natural logarithmic function. And then the 3 here is just the coefficient, the 9 is the coefficient, and the 8 and the -4. But then we also have this 2 and 4 here. And where did these come from? And it actually has to do with the 2x plus 7. So don't forget, we have a chain rule here, so we have to differentiate that inner function. So in this case, it's 2x plus 7, so we just have 2. And in this case, it's 4x minus 3. We are left with 4. And in this one, the derivative is just 1, so that's why we don't have anything here. And same with here, x plus 3, the derivative will just be 1, so that's why I don't have any additional terms here. That being said, if any of your functions were, for example, here, maybe even a bigger composite rule, so it was like x squared plus 2 to the power of 8. So for example, something like this, then you would have to do additional work. So always just double check your work and make sure that you don't have any extra chain rules that you have to apply. So always look at those inner functions. And now if I just multiply by y here, because again, we are just looking for that y prime, then, and I've just simplified here by evaluating those multiplications. Then my final derivative will be something like this. And yes, it's big and complex, but I hope you saw that the steps to achieve this was not as complex as it would have been if you were trying to do any sort of quotient rule or product rule here. And of course, you can always check this using a derivative calculator, but it really helps using the logarithmic derivative to speed up the process here and just simplify our work a lot more. Now let's look at two more examples, just quick ones, just to bring in those trigonometric functions in as well. So starting with y equals 3 to the power of sine of 3x. So again, this is an exponential function with a base of 3, and then our exponent is it's a composite function, and actually we have even like a composite function within a composite function because you have sine of 3x. 3x itself is a function as well. So we're going to do a change of variable with that exponent. We're going to let u be equal to sine of 3x. And then when we find the derivative of du by dx, we have cosine of 3x. And then again, don't forget that 3x itself needs to be differentiated. So this will just give us 3. And that's why we have 3 times cosine of 3x. Now, writing y as 3 to the power of u with our change of variable, we can differentiate with respect to x, which is, again, what we originally wanted. When we find y prime, this is just dy by dx. And that's our goal to begin with. Now, dy by dx is going to give me d of 3u by du and then du by dx, which we already found this up here, and this was 3 times cosine of 3x. So then I'm just looking for d of 3 to the power of u by du, which is going to, by our lesson, the definition in our previous lesson, be 3 to the power of u times natural log of 3. Now, again, we don't want any u's here, so we substitute back our definition there with u equals sine of 3x, and our final answer will be 3 to the power of sine of 3x times natural log of 3, and then 3 times cosine of 3x. And then I've simplified this to this expression here, and take a moment to think why this looks like this. And the reason for that is this 3 here. All I've done is use the property that 3 times natural log of 3 is the same as 3, or sorry, natural log of 3 to the power of 3, which is natural log of 27. And you may choose to not do that step, but again, it's just to show you another form that you can write it as, just to simplify how many numbers you perhaps have in there. So now we don't have a coefficient, we just have the 3 terms there. And our last example, we have y equals log of secant of x. Again, change a variable here. We're going to let our inner function, which is secant of x, equal to u. And the derivative du by dx is going to be, and remember secant is just cosine of negative 1 x, so our inverse function of the cosine function. And so using power rule here, we have d of cosine of x by dx, and then in our denominator we have cosine of x to the power of 2. And this part here is just negative sine of x, and then my denominator there. And this, I've just split it into 2 parts, which is going to give me tangent of x times secant of x. And so We are going to see why this is going to help us as well shortly. So now taking the derivative of both sides, we have y prime on our left-hand side, and then on our right-hand side, we had log of u. So by definition, this is 1 over u, and then the natural log of 10. And the 10 here comes from the fact that log of u is actually log base 10. When we just don't write anything, there is a base 10 there. And so now substituting back that value of tangent of x times secant of x here for our derivative of du by dx, we are going to get this expression here. And the secant of x just came from that u. So now I can simplify those two secants together, and I'm left with tangent of x over the natural log of 10. And that is my derivative. And I hope you've seen how the derivative of logarithmic functions can be helpful, not just for themselves, like differentiating exponential and logarithmic functions, but also when differentiating certain polynomials and certain rational functions, as well as trigonometric functions. And that is the end of our lesson. So please complete the practice questions here and check Google Classroom for any additional tasks. And I will see you all next class.